This is one line of C. You can read every word of it. Compile it, the whole function comes back as two numbers. The word add is nowhere inside either one. The first one's a 9-digit number, and that number is the whole of your addition. The second one just says go back to whoever called you. That number came out of a compiler. A compiler is the program that turns what you typed into something the chip can run, and nothing else reads your text on the way. But it did not translate the word add. Nothing in that number is a word at all. So the question is not how the computer understands what you typed, it is how your line became that exact number and why that one. Somebody has to turn text into numbers. For the first years of computing, that somebody was a person. Before 1954, almost every program was written the machine's way. One step for every single thing the machine does. In the machine's own order, with the person keeping track of where every number was kept. Getting it right was the job. In 1949, that job caught up with Maurice Wilkes. On the stairs of the Cambridge Computer Lab, he was walking between the machine and the punch, where a program became holes in a strip of paper. He wrote later that it hit him on those stairs. A good part of the rest of his life was going to be spent finding errors in his own programs. That was one man on a staircase. John Backus at IBM later put numbers on what it cost everybody. In 1954, the programmers at a computer center cost at least as much as the computer did, and a quarter to a half of the machine's own time went on finding mistakes. Writing programs and fixing them ate as much as three-quarters of the cost of running a computer. The fix you might already be thinking of is the one they tried. Let a program sit inside the machine, read something friendlier than numbers, and work your program out as it runs. Systems like that were running by 1954, and every one of them slowed the machine down by a factor of 5 or 10. Those machines were rented. A program that ran 10 times longer used 10 times as much of the machine you were renting. So you could have easy writing and slow running, or painful writing and fast running. Backus went after a third option. His team's program would make the numbers once before anything ran and then get out of the way. The numbers had to come out almost as fast as the ones a person wrote by hand. He was blunt about why, at half the speed of handwritten code, nobody would use it. That program was FORTRAN. It arrived in April 1957. By the end of 1958, on the machines that had it, more than half of what they ran came out of the program instead of a person. That deal is the one your compiler still keeps. It makes the numbers ahead of time and it isn't there at all while your program runs. That sounds backwards to me, so I'll say it plainly. The three things your line is about to lose are not the compiler being careless with your work, they are the price of the speed. Because a number is the only thing the chip ever gets, and it gets it in one form: 32 bits, 32 switches, and each of them is either on or off. On this machine, that row of switches is the part of your function that adds. That row is doing four separate jobs at once because each stretch of it is wired to something different. The 11 switches on the left are what to do. The next 5 say, take a number out of slot 0. A slot is a numbered place this chip keeps a number in. And the two you handed your function are in slots right now. 5 more further along say take the other number out of slot 1. The last 5 say put the answer back in slot 0. I have made that row sound tidier than it is because the 6 sitting in the gap are doing nothing at all here. So you can test the wiring without knowing anything else. Take the second switch from the left and turn it on. Nobody's written a line of anything. One switch moved, the number is a different number now, and this machine subtracts. Turn the switch back and it adds again. By now you might think there's a table inside this chip pairing the word add with a number. There is no table because there was never a word to look up. Those switches are wired straight to the thing that adds. I'm giving you the simple version here, and I should say so. A modern chip does much more than this before anything moves, and none of that work is reading text. But you didn't type switches, you typed 39 characters of near English. The compiler rewrote them 3 times, and each rewrite threw away something you have typed for good. You can watch all three go. A line of character doesn't come with the words marked, so the first rewrite works that out and turns them into words. The moment it does, every space, tab, and line break you chose is gone, and it can never come back. You might think something in the output must still remember your layout. Here's the same function laid out 3 ways: 39 characters on one line, 33 with the spaces taken out, 40 over 3 lines with a tab. I compiled all three the way you would actually ship them. Each one gives you a file, and all three give the same file, switch for switch, with nothing in it to say which of the three you type. Words on a line still don't say what happens first. So the second rewrite turns them into a shape, and the shape costs you your brackets. Take a line with something to argue about, a plus b times c. Write it again with brackets, round the multiplier. Exactly the way you were taught, it already works. Both lines give the same two numbers and both give the same file. So you might think brackets do nothing. Move them. Put them round the plus instead, and the number changes. And now there are three numbers where there were two. Your brackets picked the shape decided the order, and the order is the only part that reached the output. The order lives in the shape. A shape built out of your words still has your names in it, but a slot doesn't have a name. So the third rewrite takes them. This is the loss I find hardest to swallow and the easiest to prove. Rename A and B to something else. You would expect that to change something. But what comes back is the file you already had. Switch for switch, your new name is nowhere in it. Look at where A and B actually went. A became slot 0, B became slot 1. Both of those numbers have been sitting in the row since the start, written out in switches. Your spacing went when your characters became words. Your brackets went when those words became a shape. Because the shape already knew what happens first, your names went when the shape became switches. Because a row of switches has slots instead of names. So look at the number again, and this time you can read your function out of it. The 11 switches on the left are your plus sign. The next 5 are the slot that A became, and 5 other along are the slot that B became. The answer comes back into the last 5. That number is not a name for adding two numbers. It is the pattern that turns on the switches that add them. The understanding was all yours, the compiler spent it. You might think nothing you typed survived any of that. One word did, and it's the one I would have bet against. Look at what the compiler actually wrote. Your whole function is 64 switches long, and the file it came back in is 4096 switches. Somewhere in the rest of them, spelled out in plain letters, is the word add. Not in the two numbers, those are still exactly what I said they were, and nothing in either of them is a word. Your word is sitting in a part of that file that never runs. Rename A and B, and the file doesn't change at all. Rename the word add, and it does. The two numbers come back exactly the same, and now nothing else can find them. That's what the name is for. Your name for the function sits on a list of its own, kept apart from the switches. Because something outside this file has to be able to ask for the function by name. A slot never needed a name, a function does. Three of the things you typed were destroyed. One was kept, and not because it meant anything, it was kept because something else has to call it. Next time you spend 10 minutes lining your code up, you know exactly who you are doing it for. Your spacing did one job on this line. It showed the first rewrite when one word ended and the next began. Everything after that is for you. Alright, if you like the video, make sure you like and subscribe. Thank you for watching.